Welcome to iLectureOnline, and this video and the next, maybe 10 more, is based on a special request. Some of the viewers have asked if I could do something on angular momentum, and I went through all my videos, and sure enough, there were no videos on angular momentum, so here we are. Video number 1, angular momentum. Let's talk about some basics of angular momentum. So before we talk about angular momentum, I want to go do a quick look back at what linear momentum is. Remember, the definition of linear momentum, P, we use P for linear momentum, is that it's a product of the mass times the velocity of an object moving in linear motion. Now, that's not really like what energy is, because when you try to calculate the kinetic energy of an object moving in linear motion, it's 1/2 mv squared. And the difference between momentum and energy is that when two things collide, they end up with a total energy that is less than the energy they usually started with, unless there's a perfectly elastic collision, which of course in the real world that almost never happens. So energy is not conserved when there are collisions, but we noticed that the product of the mass times the velocity of multiple objects colliding with each other, if we add up all the linear momentum of all the objects before the collision, and then we add up all the linear momentum of the object after the collision, turns out that those two sums are equal to each other. In other words, linear momentum is conserved in all collisions. Now, part of that is that momentum is actually a vector quantity. It's the product of the mass times the velocity, and since velocity is a vector quantity, so is momentum, which means that the direction is important. So when an object moves in one direction, it has positive momentum, let's say to the right, the way you're looking at it. And if an object moves in the other direction, it has negative momentum. But if you add up all those positive and negative momentums together, you end up in the end, all the momentums before the collision equal all the momentums after the collision. And it's very handy. So for example, a quick example here, we have a small mass of 5 kilograms moving to the right at a positive 10 meters per second. We have a bigger mass, 20 kilograms, moving to the left at minus 5 meters per second, minus because it's to the left. And so when they collide, and let's assume they stick together, what is their final velocity? And then of course you can say that the initial momentum of all the objects moving equals the final momentum of all the objects moving. Initially we have the first mass moving at initial velocity v1, the second mass moving at initial velocity v2, and when they collide and stick together, the masses are then together and they have some sort of final velocity. If you then algebraically solve for final velocity and plug in the numbers, you get a final result. So you know that together they move to the left at minus 2 meters per second after the collision. And how do we know that? Because momentum is conserved. It turns out there's such a thing as linear momentum. I mean, not linear momentum, I meant angular or rotational momentum. So angular momentum is kind of like rotational momentum. It's momentum that's ascribed to an object that's rotating. Now, for example, I have two disks here, and let's say that their axes are coaxial, so that the one is directly above the other via the axis. And let's say that the object on the bottom is rotating in a counterclockwise direction, and the object at the top is moving in a clockwise direction. Now notice their center mass is not moving anywhere, they're staying put in place, but they're actually rotating about their axis. Because of that, they also have what we would call momentum. But it's not momentum because they're moving along a straight line, it's momentum because they're rotating, they're revolving around an axis. And so, because of that, you can think of it as an object that's moving in a linear sense. It takes some effort to slow that down or to make it speed up. Well, same with rotational object. An object that's rotating, it would take some effort to slow it down or take some effort to make it speed up. So it's it's almost akin to energy, but not quite. It turns out that if we express their rotational momentum somehow in a mathematical sense, we can then say that no matter what happens, let's say you take those two disks and plop on top of each other, the final angular momentum of the two disks together must equal the initial momentum of each disk separately added together. So in other words, angular momentum is also conserved. And when we say it's also conserved, it is always conserved 100% of the time. Angular momentum is always conserved, just like linear momentum is always conserved. So what does an equation look like for angular momentum? Well, notice for linear momentum we have P, linear momentum, equals the mass times velocity. So what are the rotational equivalents of mass and velocity? Now, since we already dealt with moment of inertia and rotational kinetic energy, we've already seen that relationship, and it turns out instead of mass for linear motion, we use moment of inertia for rotational motion. So the angular momentum L stands for angular momentum or rotational momentum, that is equal to, instead of m, mass, we use I for moment of inertia, and instead of linear velocity v, we use angular velocity omega, the rate at which something rotates around. And so this is our new equation for angular momentum, just like we had a linear equation, P equals mv. Now again, this is a vector quantity, so technically speaking, we should write it like that. So angular momentum L is equal to I times omega. Omega is the angular velocity, which is also a vector quantity because it's directional. And by definition, if something rotates around in a counterclockwise direction, we call that a positive angular velocity. If something rotates in a clockwise direction, we call that a negative angular velocity. So it does have direction, clockwise or counterclockwise, and so therefore we write L as a vector quantity. Now, how does a rotating object have direction? Well, it's like this. If you take your right hand and you make your fingers curl in the direction of the rotational motion like this, your thumb will point in the direction of the angular momentum vector, which means in this case the angular momentum vector is pointing upward. So let me use a red color for that. So that means that in this case the angular momentum vector is pointing directly upward. Now, for this rotating object, take your right hand, curl your fingers in direction of rotation, and here you can see that your thumb is pointing downward. So here we can see that this object has an angular momentum vector pointing downward. So here, this is what we would call a negative angular momentum vector, and this is a positive angular momentum vector. The faster it rotates, the longer this vector becomes, the greater the moment of inertia, the longer this vector becomes. Now you see this is a much bigger disk, so it has a bigger moment of inertia, and it's rotating faster than this disk right there, so you expect a larger angular momentum vector, and this disk is smaller and rotating slower, so expect a smaller angular momentum vector. Now, when you take the top disk and you plop it right on top of the bottom disk, axis to axis, then of course the speed of rotation will change. Now, since one is in rotating the opposite direction than this one, they will kind of counter each other, and the resulting angular momentum will be probably something smaller. I would guess that if you add this vector to this vector together, you end up with a smaller vector. So you can think of it this way, that this is kind of a vector addition, and so that this vector added to this vector will end up with a smaller angular momentum vector at the end. And so that's how we also use angular momentum vector to have kind of a summation of two objects rotating that collide with each other or that end up on top of each other, and so their total angular momentum will therefore change. Well, I shouldn't say that. The end result will be have a different angular momentum vector because of the sum of the two initial angular momentums. So we're going to use the same thing as we did here. We can say that L initial equals L final, so that again, angular momentum, the sum of all the angular momentums before the collision equals the sum of angular momentums after the collision. So now we can say that I times omega 1 initial, this is I1. So let's call this disk 1 right here. And, well, I'm using Roman numerals. Let's just call this disk 1 and disk 2. So plus I omega 2 initial, this is I2. And let's assume that they now stick together just like in our example there. So we can then add the two moment of inertias, I1 and I2, times omega final. And of course, what we want to do here is find omega final. So omega final is equal to the initial angular momentum, which is I1, omega 1 initial, plus I2, omega 2 initial, all divided by I1 plus I2. Now, remember, what is the moment of inertia of a spinning disk? Well, the moment of inertia of a solid spinning disk is 1/2 the mass times the radius squared. So in each case, we'll have to take 1/2 the mass times the radius, and let's plug that in here. So this is equal to 1/2 times the mass of the first disk, which was 4 kilograms, times the radius squared. The radius is 50 centimeters, which makes it 0.5 meters. So 0.5 meters squared Oh, not yet. We're not done yet. Now we have to multiply times the angular velocity, which we said was 4 radians per second, positive. So times 4 radians per second. Now technically we don't have to write the word radians, but I always do just to make it easy. Radians is a non-unit. And then we add to that the moment of inertia of the second disk. So we have 1/2 times the mass. The mass of the second disk is 2 kilograms. Times the radius squared. The radius is 30 centimeters, so that's 0.3 meters squared out, and times the angular velocity, it's a negative 2 radians per second. All right, now we have the top portion. Now we divide by the bottom portion, which is simply the sum of the two angular momentums, which would be 1/2 times 4 kilograms times 0.5 meters squared. There's a decimal there. Plus 1/2 times 2 kilograms times 0.3 meters squared. Excuse me. All right, so all we have to do now is work that out. I've got a calculator right here. Maybe we can do this without a calculator. 0.5 squared is 0.25 times 4, that's 1. Times 4 is 4, times 1/2 is 2. So this is equal to 2. This is going to be a minus, because the minus over here. 2 times 1/2 is 1. Times 2 times 0.09, that's 0.18, so that's minus 0.18, all divided by the denominator, which is, that would be 1/2, and this would be 0.09. So that would be 1/2, and 0.09 would be 0.59. Maybe I should check that with a calculator real quick. Make sure I did that correctly. And that's 0.9. All looks good. All right. So this would be equal to 1 point, and of course, what are the units? Units, of course, would be radians per second. Radians per second. And so that would be 2 minus 0.18 divided by 0.59. And it would be a positive 3.08 radians per second. All right. So there's a really good example of how we deal with angular momentum. Again, angular momentum is simply the product of an object's moment of inertia and angular velocity. Angular momentum is conserved in a collision. Two spinning disks, one in this direction, the other one in the other direction. Plop them together, now they stick together. And so what is their final angular momentum? It seems to make sense that it would be somewhat less than this, but not negative, because this is a much smaller disk with a much smaller moment of inertia, but enough to slow it down significantly, so now it's only about 75% of its original rotational speed. And that's a very good example and an explanation of what angular momentum is.